I mean, you hit print in a document and poof, it just works. But why can't your word processor just, talk directly to the printer? Why does it need this invisible middleman? It seems so simple. But the answer to that question gets to the very heart of how your computer keeps itself from falling apart.
All right, welcome to the Explainer. Today, we're going to pull back the curtain on one of the most fundamental concepts in all of computing: system calls. Think of them as the gatekeepers, the traffic cops, the secret translators that make everything you do on your machine actually possible. Let's see how they do it.
So here's our game plan. First, we're going to look at the two separate worlds living inside your computer. Then we'll see how they actually talk to each other. After that, we'll check out the menu of services they can request, look at a few specific orders, and finally, we'll wrap it all up with why this entire system is so incredibly important.
Okay, let's dive right in with our first section: the kernel's velvet rope. The best way to understand how your computer stays stable and safe is to picture it not as one big open space, but as a really exclusive club with a very, very strict VIP section.
So, on one side of that velvet rope, you've got your everyday apps, your web browser, your games, your music player. They all live in what's called user space. They have very limited privileges, and they are absolutely not allowed to touch the hardware directly. On the other side, inside that fancy VIP lounge, is the operating system kernel. You can just think of the kernel as the boss. It has total, unrestricted access to everything: the CPU, the memory, that printer, you name it. And this, right here, is the golden rule. For a regular app to do anything important, like saving a file or, yes, printing a document, it can't just go do it. Nope. It has to politely walk up to that velvet rope and ask the kernel, the boss, to please do it for them. This whole setup is what prevents a single buggy or malicious app from bringing down your entire system.
Okay, so how does a program officially ask for this kind of help? Well, that brings us to section two: making a system call. As you might guess, there's a very formal, very structured way to make these requests.
So, what is a system call exactly? It's the official mechanism, the procedure, that a program uses to ask the kernel for a service. It's the official language for talking to the boss. And it's not a suggestion, it is the only way to get these important jobs done. The key word here is interface. A system call isn't just some random command. It's the safe, controlled bridge that connects those two separate worlds we just talked about: the limited everyday app and the all powerful kernel. Right, so if a program's going to make a request, what's even on the menu? What can it actually ask for? That brings us to section three: the service menu. Turns out the kernel offers a pretty specific list of services. And believe it or not, pretty much all the thousands of possible requests can be neatly sorted into just five main categories. First up, you've got process control. This is all about starting, stopping, and just generally managing programs. Then there's file management, which is exactly what it sounds like: creating, opening, reading, and writing files. Device management is how you talk to things like your printer or your hard drive. Information maintenance is for asking simple questions like, hey, what time is it? And finally, communication, which lets different programs running at the same time talk to each other. All right, we've seen the categories on the menu. Let's go ahead and place a few specific orders and see what some of the most common system calls actually do. So, let's say a program needs to create a brand new running process. To do that, it uses the fork system call. And what this does is actually super cool. It creates a nearly identical clone of itself called a child process. Think about when your web browser opens a new tab. That's often starting out as a new process. Suddenly, you've got two running where there used to be just one. And a lot of the time, what happens next is the original parent process will use another call: wait. This basically tells the parent to just hit pause, take a break, and wait until its child has finished whatever task it was created for. It's a really clever way to manage and sync up work. Now, execute is a different beast altogether. It doesn't create a new process. Instead, it completely transforms the current one. It basically wipes out the program that's running and loads a totally different program into its place. It's kind of like a stage actor leaving the stage and a completely new actor coming on to perform a different play, but in the exact same spot. So, what about something simple, like reading a file? Well, that's a two-step order. First, the program uses the open system call. The kernel checks for permission, and if everything's good, it hands back this special ticket called a file descriptor. Think of it like a code check number. Then the program uses that ticket with the read system call to actually pull the data from the file. And finally, when a program is all done with its work, it does the polite thing. It calls exit. This is just the program telling the kernel, hey, I'm finished. You can have all my memory and resources back now. It's the official, clean way to shut everything down.
And that brings us to our last and honestly most important section. Why does any of this matter? Well, at the end of the day, it's about creating a stable, orderly society inside your computer. I mean, just stop and think about it for a second. Imagine a world with no system calls. Programs couldn't start other programs, you couldn't save a file, you couldn't print anything, nothing could talk to anything else. It wouldn't just be a little inconvenient, the entire system would be pure, unusable chaos. And that, right there, is the whole point. System calls are the absolute foundation of stability. They provide that essential, controlled access to the computer's resources. They protect the hardware from misbehaving programs and make sure that everything can share and work together smoothly and safely. They are the rules of the road that make everything else possible. So, we've laid out the system and all the rules that keep it in order. And that leaves us with one final, pretty important question to think about. Now that you know the rules, what happens when a program tries to break them?